The James Webb Space Telescope has achieved something previously thought to be impossible. It captured data from within a black hole, something humanity was never meant to witness. This wasn't a theory or a simulation, it was real, observational data. What it revealed has left physicists astonished. The observations appear to defy our current understanding of space and time and suggest that black holes may not simply be the final resting places of matter but could potentially serve as gateways. This discovery, if validated, could fundamentally reshape not only our understanding of black holes but the entire framework of the universe. For over 100 years, black holes remained some of the most enigmatic objects in the cosmos. Immense, invisible entities that consumed everything in their path, even light itself. We had ample evidence of their existence: stars that vanished, gas that radiated extreme energy near them, and a famous blurry image of one taken in 2019, but no one had ever seen inside a black hole until now. That changed when the James Webb Telescope turned its infrared sensors toward the center of a supermassive black hole located 55 million light-years from Earth. Initially, what it detected was expected: gas spiraling inwards, high temperatures, and the familiar radiation signature of matter falling into a gravitational abyss. But deeper within the data, something unexpected emerged. The telescope detected distortions that didn't align with known physical patterns: light bending unusually, space itself rippling, and most astonishingly, a single pulse. This wasn't ordinary radiation. It was a brief, coherent signal, a flickering pattern of light that occurred once and then vanished. The scientific team scrutinized it, ran simulations, and checked past observations, but the conclusion was clear: the telescope had recorded something right at the edge of the event horizon, the very boundary where light is traditionally trapped forever. This wasn't a digital mock-up, it was real. Though the telescope didn't peer into the central singularity, no instrument can it glimpsed what we believed impossible: structural detail where there should have been none. Rather than a featureless void, the black hole revealed complexity layered. Regions interacting with matter in ways that seemed to twist space, contort time, and pull in surrounding material in a strangely ordered flow. That pulse of light, it wasn't a message, but a repeated signal, flickering briefly at the very edge of darkness, like a heartbeat. Just one beat, then gone. Scientists still can't fully explain its origin or meaning, but what's clear is that we have, for the first time, seen tangible signs of activity from within the black hole's boundary, evidence that the edges of these cosmic objects are more dynamic and perhaps more alive than ever imagined. And this could be just the beginning. This pivotal moment in astronomy was built on over a century of theoretical work, beginning in 1916 when Albert Einstein introduced his general theory of relativity. His equations suggested a scenario where space could collapse so intensely that even light could not escape, a concept that would later be known as a black hole. At the time, few believed such entities were physically real. The scientific community treated them as mathematical curiosities, but that began to change in the 1960s when astronomers observing the Cygnus constellation noticed something unusual: a bright blue star orbiting an invisible partner. That partner, dubbed Cygnus X1, was drawing in matter and emitting X-rays, a clear indicator of extreme gravitational forces. It became the first widely accepted observational evidence of a black hole. As decades passed, more black holes were identified, not only stellar-sized, but also supermassive ones residing at the centers of galaxies, some weighing millions to billions of times more than our Sun. In 2019, the first image of a black hole's event horizon, glowing gas and dust forming a bright ring, was released. Though indistinct, it confirmed that black holes weren't just theoretical, they were real and widespread. Yet, despite these advancements, one fundamental mystery remained. What lies inside a black hole? That's where the James Webb Telescope came in. As the most advanced space observatory ever constructed, it succeeded in 2025 where none had before. Not only did it observe a black hole's edge, it saw through it, capturing bent light, distorted space, and potentially glimpses of what may lie beyond. Webb's observations point to a complex, layered structure within the black hole. Scientists identified three main regions. The first is the event horizon, the boundary beyond which nothing escapes. It is the line where space and time themselves begin to warp into something unrecognizable. The second is the photon sphere, a zone where light doesn't immediately fall inward but orbits the black hole, circling like water in a drain. Webb's data showed light being disrupted in ways never recorded before, suggesting unseen forces affecting it from within. Then comes the core of the singularity. While Webb didn't directly observe it, it picked up something nearby, gravitational ripples moving faster than expected, seemingly without any source. This could indicate the black hole is dynamically interacting with its environment in unknown ways. Some researchers suggest Webb might have caught a black hole feeding, drawing in matter in real time, twisting it into energy patterns that defy randomness. One of the most astonishing observations was of an object undergoing spaghettification, a term used to describe how matter is stretched into long strands by a black hole's gravitational forces. For the first time, this wasn't just theory. Webb captured what appeared to be a neutron star fragment being pulled apart, its shape distorting until it was reduced to a thin filament before disintegrating completely. The telescope even recorded time dilation from Earth's perspective. The object appeared to slow down as it approached the event horizon, eventually seeming to freeze in place, a known but rarely visualized relativistic effect. Even more puzzling, Webb detected gravitational echoes, subtle ripples that bounced back from the black hole's edge, unlike anything produced by stars or galaxies. This suggested that space itself was reacting in new, unfamiliar ways. These findings have revived an old idea. What if black holes aren't endpoints but openings? Could they be wormholes, tunnels through space and time? Until now, this concept was purely speculative. But Webb recorded something unexpected, light appearing to emerge from near the black hole rather than being absorbed or reflected. This defied established physics. Some believe the telescope may have observed a rapidly spinning black hole or a Kerr black hole. In theory, such an object doesn't collapse into a single point but stretches into a ring-like structure, potentially creating a passage through spacetime. Webb's images revealed high-energy light that didn't match any known source. Its path seemed to come from behind the black hole, possibly from another side altogether. Whether it was gravitational lensing, reflection, or something else entirely remains uncertain, but the implications are profound. If even a part of a black hole functions like a wormhole, it could mean that travel across time or dimensions isn't forbidden by physics, it's permitted. Adding to the mystery is the possibility that black holes aren't solid objects at all, but illusions, three-dimensional effects produced by two-dimensional information. This is the basis of the holographic principle, a theory gaining new traction due to Webb's data. It suggests that everything happening inside a black hole, the gravity, radiation, even the singularity, is actually encoded on its outer surface, much like a hologram. Physicist Enrico Raldi has explored this using quantum matrix models, showing how black holes in such models behave like holograms. Webb's radiation readings confirmed this. Instead of seeing signals from deep within, the telescope observed structured patterns emanating from the black hole's edge. It was like watching a 3D movie projected onto a 2D screen. This could mean that the true laws of physics reside not in the depths of space but on its surfaces, and possibly that the entire universe functions in the same way. To explain these phenomena at a deeper level, some researchers are turning to string theory. According to this theory, everything in existence from photons to black holes is made of vibrating strings, operating in up to 10 dimensions. Webb detected high-frequency vibrations near the black hole, unlike anything seen elsewhere in the cosmos. These pulses might be the signatures of strings resonating in dimensions beyond our perception. If this interpretation holds, then black holes might not simply be collapsed stars but tunnels to higher dimensional realms. In some versions of this theory, our universe could even have originated from a black hole in another universe cosmic. Offspring birthed through interdimensional collapse. So, what now? The scientific community is buzzing. Experts worldwide are poring over Webb's data, frame by frame. Some call this the most important discovery since the Higgs boson. Others believe it could lead to a long-sought theory of everything. Not all information has been made public. Whispers suggest that agencies like NASA and ESA are holding back further revelations, perhaps for validation, or perhaps because the implications are too vast to digest all at once. And then there's the looming question, are we in danger? At present, the nearest known black hole is 1,500 light-years away, far enough not to pose a threat. But Webb's data shows that black holes evolve. They grow, they merge, they shape. Galaxies, the universe is changing, and black holes may be key to that change.